So now let's look at shortest paths in graphs where we allow negative edge weights. In particular, let's look at the Bellman-Ford algorithm. So recall that the correctness for Dijkstra's algorithm relied on an invariant property that every vertex that we burn automatically has the shortest path computed at the time when we burn it. However, as we saw, this argument doesn't work if we can have negative edge weights, because we may find later a path via a vertex which we have not burnt yet, which becomes a shorter path to a vertex we have burnt earlier. We also said that allowing negative edge weights is one thing, but allowing negative cycles is not a good idea, because once you have a negative cycle, you can go around the cycle as many times as you want and arbitrarily reduce the length of the path. So the shortest path is not even a well-defined quantity. So long as we have negative edges but not negative cycles, shortest paths do exist and we can hope to compute them. So let's first look at two basic properties about shortest paths, which hold regardless of whether the edges can be negative or not, provided we don't have negative cycles. So the first property is fairly obvious, that a shortest path will never go through a loop. So supposing I want to go from S to T, right? And suppose along the way I actually go through the same vertex twice and then I continue. Now what we know is that this is a loop, right? And since it is a loop, the weight is greater than or equal to 0. It cannot be negative because we have ruled out negative loops. So therefore, if I take this path and I just cut out this loop, then I have a direct path from S to T. And if I look at the cost of the direct path from S to T, it cannot be any bigger than this one, because at best this loop has 0 and I have decreased nothing, but in the general case, the loop has some positive cost and I have actually reduced the cost, right? So shortest path never loops, so it will never visit the same vertex twice. This means that it can have at most n-1 edges, because I can only allow, so I totally have n vertices. So if I don't allow any vertex to repeat anywhere along the way, then obviously I can only have n-1 vertices, n-1 edges. Right? So there is a bound on the length of the shortest path. The other property is that regardless of how the shortest path looks, right, along the way every path that makes up the shortest path is itself a shortest path. So for instance, if I have a path like this from S to T, which goes through some intermediate vertices V1, V2 up to Vm, then if I look at the path only up to Vm, then this is the shortest path from S to Vm. There cannot be any shorter path, because supposing there was another shorter path, okay, suppose there is a shorter way to get from S to Vm, then I can take this, and the red path now will be shorter than the green path. Right? So therefore the fact that I am going to T via Vm and this is the shortest path means that there must also be only this much of a short path from S to Vm, and this holds at every point. So again, for example, S to V2, this must be the shortest path, because otherwise if there were a shortest path, then I will take that shorter path and then I will add on this path which I already have, and I will get a shorter path to everything from V3 onwards. Right? So every prefix of a shortest path is itself a shortest path. So these two properties are enough for us to arrive at the Bellman-Ford algorithm for shortest paths in the presence of negative edge weights. So to get to the Bellman-Ford algorithm, we have to analyze a little bit more about what is happening in Dijkstra's algorithm. So in Dijkstra's algorithm, whenever we burn a vertex, whenever we visit it, we update all its neighbors. Right? So we update the distance of when we burn a vertex j, we update for every edge jk, right? We update the distance to k to be what distance we already know for k, together with the distance to j and the edge from j to k. So we have a newly discovered distance through j perhaps, and we compare it to the distance we already know and we keep the smaller of the two. So let's call this operation an update, right? Updating k from j. So in Dijkstra's algorithm, we only do this update when we burn j. And the correctness of Dijkstra's algorithm says that when we burn j, the distance to j is the correct distance to j. Right? So what we have seen is that in the negative edge weight case, if we use the strategy of Dijkstra's algorithm, this may not be the case. That when we burn a vertex, just because it's in the shortest expected distance among the unburned vertices does not guarantee that this is the correct distance. Right? We might find later on a smaller distance. But in spite of this update operation has some useful properties which we can exploit. So the crucial thing is that the update gives us an upper bound on the distance to k. Right? we already have, so at any point the invariant that we have is that the value that we have in distance to k is greater than or equal to the actual shortest distance from the source to k. Initially we may assume it is infinity, so that is surely greater than the actual shortest distance. At any point when we reduce it because we have found a concrete path which gives us a shorter distance. Right? So when we do this, after this update, we know that the distance to k is no more than the distance we have just discovered through j. Because if it was already less, then we keep it that way because we found it through a previous j prime, or we have found it now, in which case we have updated it in this update operation. This also means, because of our previous observation about shortest paths, that if actually on Dijkstra's algorithm also, that if distance j is actually correct, and the shortest path now consists of just adding this edge, okay, we are not claiming it is, but if it is the shortest path, then the distance to k will be correctly computed. Okay. So in a nutshell, this update operation is a safe operation because it will never bring distance of k below the actual value. So it will always be above the value that we want. So we can keep doing spurious updates or unnecessary updates and it doesn't hurt us. Okay, so redundant updates cannot upset this calculation. It just may not make progress, but it will not send us to a situation from which we cannot recover the minimum cost. Because we will always be at or above the minimum cost. So whenever we do a min, we will always be coming down but not crossing below the actual value we want to find. So if we look at Dijkstra's algorithm, then what it does is a particular sequence of greedy updates. Right? It chooses the smallest distance vertex which is not burnt and burns it. And our proof breaks down because this sequence does not necessarily give us the shortest path if the weights can be negative. So a natural question to ask is, what sequence of updates should I do in order to actually get the shortest path? Is there a better way of computing this, the sequence of updates rather than going via the greedy heuristic of Dijkstra's algorithm? So suppose we have two vertices s and t. We want to find the shortest path from s to t, and suppose there is a shortest path, okay, which goes via v1 to vm as we have seen before. Now, if we do the updates in this order, that is, we first compute the update from s to v1, then we compute v1 to v2, then we compute v2 to v3. In between, we can do other things. It's only that these updates happen in this sequence. Then v3 to v4 and so on, and finally we do vm to t. Then what do we know? Well, we knew earlier that if we had correctly computed the distance up to s, then this update will correctly compute the distance up to v1 because this is the second last node on this, right? So if distance of j is correct and j is the second last node on the shortest path to k, distance of k is correct after the update. So because distance of s was 0 and it was correct, when we do update SV1, this distance becomes correct. Now we might do all sorts of other updates which don't bother us. But now when we come to V2, we will be updating V2 from V1, and V1 is the second last path and this shortest path. And therefore this also becomes a correct value. And then this also becomes a correct value. Right? So in the middle of all these updates, if we identify this particular subsequence of updates, S to V1, then V1 to V2, then V2 to V3, then we have got the distance. Okay? So now the question is, how do we make sure that we have this sequence of updates for S and T? So Bellman-Ford algorithm basically says, don't try to find a particular sequence, just generally compute all possible sequences of updates. So at a high level, this is the algorithm. It says initially assign the distance of S to be 0 and the distance of U to be infinity for every other vertex. Now you just blindly do every update n-1 times. Right? So what you do is initially you update for every edge, given the fact that S has distance 0 and U is infinity otherwise. Then we update everything. So all of these updates where S is the source vertex and V is the target vertex, these will give us now some finite values for these V's, whereas these will just remain infinity, right? So this will become finite and these will become infinity. Now you have done one full sequence of updates in which other than S, all the neighbors of S now have some finite values. Now you do this whole thing again. Right? So you update every edge again. And then you update every edge again. Now we know that a path, shortest path between any two vertices has at most n-1 edges. Therefore, if we do this thing n minus 1 time, the claim is that if I want any sequence of updates, I might find a sequence of updates which goes like this, or I might find any sequence of n minus 1 updates which is a legal path will be represented in this. Okay, so this is a very clever matrix which has all the updates after one iteration, all the updates after two iterations. Now if I want a particular sequence for update E1, then update E2, then I will find E1 here, then I will look for E2 here, then I will find E3 here, and then so on. Right? So every possible path is represented. In particular, given our example here where the path goes from S to V1, V1 to V2 and so on, then we find that the first update comes in iteration 1. Then after having updated V1, the next iteration V1, V2 gives us the correct distance to V2. Iteration 3 will give us V2 to V3 and so on. And finally, iteration n-1, actually this may not be n-1, it depends on the length of this path. So if this path actually has n-1 steps, then the last one will give us the update from Vm to T and the correct distance for T. But this could actually be even less than n-1 if the path is of lesser length. So the algorithm is actually remarkably simple. Right? You start from a source vertex S. So initially you assign the distance to be infinity for every vertex and you initialize the distance of S to be 0. Now n-1 times you blindly repeat the following operation. For every edge in your graph, apply the distance update. So you take the distance of the target of that edge to be the minimum of the current distance for that target or the distance to the source of the edge plus the weight of the edge. Right? So we just blindly do this n-1 times, and because of this property that you will find for every valid shortest path, you will find a sequence of updates which matches that path in this sequence that you are computing here. You will always get the shortest path to every other vertex starting from S. So let's look at an example and see how the Bellman-Ford algorithm actually works. So here is a graph which has some cycles and it has some negative weights, but there are no negative cycles. So for instance, you'll see that here we have a cycle whose weight is -2 plus 1 is -1 plus 2 is +1. Okay. Similarly, here we have a cycle whose weight is, if you go around from 6 to 3 to 4 to 5, you have -2 plus 1 is -1 plus 3 is +2 -1 is +1. Right? So this is again a cycle of +1. So there are negative weights but no negative cycles. And now in this we want to compute shortest paths from 1 to every other vertex. So 1 is our source vertex. So we set up this iteration. So in the initial step we set the distance of vertex 1 to 0 and everything else is infinity. Now we will, in the first step, try to update all neighbors of things that we have here. Now all values which are infinity will not update their neighbors, but the value of 1 will. It has two neighbors, right? 2 and 8. So these two things now become finite values, 10 and 8 respectively. Now we have these three vertices which are got finite values. So you would expect that their neighbors, namely 7 and 2 has a neighbor 6. So the only outgoing edge from 2 is 6, the only outgoing edge from 8 is 7. So you'd expect 7 and 6 to get updated. And indeed, in the next step, you find that 6 and 7 get values which are updated from those values. So 8 plus 1 is 9, 10 plus 2 is 12. Now having got this, you will find that we have now updated 1, 2, 8, 7 and 6. Now notice that I now have another path, not this path from 1 to 2, right? But I have a path which goes this way from 1 to 2 via 7, and this becomes a smaller path because of this -4, right? So in this iteration, I will actually find the first non-trivial update which will violate the Dijkstra assumption that all burnt vertices are invariant, right? So the distance to 2, which was already computed to be 10, will actually shrink. In addition to that, of course, because we have new neighbors of 6, so 6 will now give us a new value for 3 and so on. So in this iteration, I find, as I said, that the value of 2 reduces, the value of 3 becomes something finite. Notice the value of 6 itself changes. Why? Because earlier we were looking at a path like this, and now we have discovered that there is actually a better path like this, which has also a negative edge to add to the benefit. Okay, so we come down from 12 to 8 plus 1 minus 1 is 8. So we continue like this. At the next step, the path to 3 shrinks further. Okay, and that's because now having got a better path for 6. So in the previous path we said, oh, the path to 6 was 12 and 12 minus 2 was 10, right? Now we said, oh, it's not 12, it's 8. So 8 minus 2 is actually 6, right? So we've got a better path to 3. We have discovered a new path because we had a path to 3 from 10 plus 1 is 11 and so on. Okay. So we continue one more step, and then because now we know that 4 was reachable in 11 steps, 4 plus 3 is 14, so 5 is reachable, but 4 itself now, because the value of 3 got updated, so the value, in this iteration the value of 3 gets updated from 11 to 7. This will get propagated after one more iteration, so now this value comes down from 14 to 7 plus 3. But in this process, what has happened is that the value of 3 has itself gone down one more time, right? So its value again reduces the value of 4. And then finally, after the n minus 1th iteration, we get a stable set of values. So these now turn out to be the shortest paths to all the vertices from the start vertex 1. So what is the complexity of this algorithm? Well, we have this outer loop. So we just run this update n minus 1 times. So it runs order n times. And now in each loop, we basically blindly update every edge. So we have an adjacency matrix. We have to identify the edges. The only way is to look at every entry, and wherever we see an entry, we take that jk and we update it. Okay. But in an adjacency list, we have exactly the edges that we want, right? So we have 1, 2 up to n, and we have exactly the edges. So we can do this update in order n time. So if we use an adjacency matrix, just identifying which are the edges takes us order n square time, because we have to probe every entry in the adjacency matrix. Adjacency list, we can do it in order m times. So therefore, if we use an adjacency matrix representation, overall Bellman-Ford algorithm takes n cube time, whereas with an adjacency list representation, we can reduce it to mn, and so if therefore the number of edges is small, this is going to be a much better solution than n cube.